for the opportunity to speak here. Okay, so I'm going to be talking about joint work with Francis Bonahon and Tian Yang. And I'm coming from this at a very topological point of view, which I think is kind of everything. I think people here have different backgrounds, so feel free to stop and ask me questions as we go along. So here's my plan, is to talk a little bit about the volume conjecture, the original version, and then I'm going to state a new one for a slightly different quantum invariant than the one for the usual volume conjecture. And then this new quantum invariant is a invariant of surface diffeomorphisms. It comes from the representation theory of the Kauffman bracket skein algebra, which is something that comes from the Witten-Reschetschken Tr of TQFT. And so I'll talk a little bit about that. And then at the end, I'll give a little bit of justification for why we think the conjecture is true. All right, so the original volume conjecture was phrased by Kashayev in, I think, 1998, using triangulations of three manifolds. And then it was quickly realized by Murakami and Murakami, maybe 2-3 years later, that you could rephrase his original conjecture using the Jones polynomial. So the conjecture relates hyperbolic geometry. So let me draw a picture. So suppose you take a hyperbolic knot, and then you color by the nth Jones-Wenzel projector, right? So that corresponds to the n plus first irreducible representation of UQSL2, if I said that correctly. And the conjecture relates the hyperbolic geometry of the knot complement, so S3 minus this knot, with the asymptotic growth of the Jones polynomial. So in particular, it says this. So if you pick this specific nth root of unity, and you look at the nth color Jones, and you look at how quickly it grows. So it's e to the something. And so that something up there is somehow determined by the volume of the hyperbolic knot. Okay. And to be honest, I have no idea where this volume conjecture comes from. It's related to physics. And for me, this is very much a mystery. Right. So I'm a topologist, right? So back when the Jones polynomial came around, I was probably still quite young, but I was alive. And it was just kind of this thing that fell out of the sky. It was used to prove all sorts of really awesome conjectures in topology, like that if it's a knot diagram is alternating and reduced, then it must be minimal crossing, right? And it just was this tool that fell out of the sky. And there was a lot of questions about where that quantum invariant came from, right? And so this is a very, very concrete answer, that this Jones polynomial is somehow detecting the volume, right? So how fast it grows is detected by the volume, is actually determined by the volume of the hyperbolic complement. The problem is that this volume conjecture has been standing for, 20 years now, and it's very difficult to prove. There's a lot of really careful analysis that you need to do, and it's only been verified for a few cases. I think Atsuki keeps on pushing the envelope, so now I think he's up to 7 crossing knots, hyperbolic knots, but still, it's hard to prove because you write down the formulas for these Jones polynomials. It's these sums, and sometimes there's recursion. There's some recursion in it, but it's hard to see where the volume comes in. And so with Francis and Tian, what we wanted to do is do it completely, to take it from a different angle, is to do another hyperbolic, another volume conjecture, but to use a quantum invariant where we know how it's related to the hyperbolic geometry from the start. Okay, so it's kind of like the hyperbolic geometry is baked in, and we have some very, very similar volume conjecture. So the volume conjecture that we propose goes like this. Suppose you have a surface sigma, and you have a pseudo-Anosov diffeomorphism. So every diffeomorphism of the surface is either periodic, meaning that the power of it is identity, or it fixes some curve, right? Or it's pseudo-Anosov, and almost all of them are pseudo-Anosov. Okay, so you pick a pseudo-Anosov diffeomorphism of the surface, and then so there's this idea of a mapping torus. So I don't know, let me try and draw another picture. Pictures never hurt. So suppose you have a surface, you multiply it by the identity, and then here you're going to glue. So you're going to glue x of 0 corresponds to phi of x of 1. So that's the mapping torus. So this is the mapping torus M sub phi. And it has a unique hyperbolic metric on it. There's a volume associated to this surface diffeomorphism. And so on the hyperbolic geometry side, we're going to talk about the volume of the mapping torus. And then on the quantum topology side, I'm going to define this quantum invariant that comes from representations of the Kauffman bracket skein algebra. And I'll do all that later, a little bit more slowly, but just so that you know where I'm headed. So there's this conjecture. Our conjecture is that when Q is some nth root of unity, then the asymptotic growth rate of this invariant for surface diffeomorphisms is determined by the volume of the mapping torus. Okay, and the idea is that somehow when we compute this invariant here, we should see a lot of hyperbolic geometry already. Okay, so then it makes it easier for this to be proven. Okay, so my idea is that for most of this, I'm going to go back and talk about this invariant, this quantum invariant for the surface diffeomorphism. And this page is going to be way lots of information. So before I can do this in quantum invariant, I should talk about what the Kauffman bracket skein algebra is, how it's related to SL2C character variety. And the SL2C character variety is like, has a copy of the Teichmuller space inside. And so it has a lot of the hyperbolic metrics are all inside there. And then there's a correspondence between representations of the skein algebra and the points in the character variety with some extra choices. And so this is where I say the hyperbolic geometry is baked in because we have this theory already. And then there's like a few steps that I need to do and then I get the invariant at the end. Okay, all right. So the Kauffman bracket, actually, before I launch into this, do I have any questions at this point about the volume conjecture? Or the statement of the, no? Okay, all right. All right, so the Kauffman bracket skein module of the, was rigid, so there was the Jones polynomial, then there's the Kauffman bracket, and then we wanted to generalize the Kauffman bracket for all three manifolds. And so this is a definition due to Tryov and Pershidsky independently. And so what we do is that in this three manifold, you look at all the possible framed knots and links. So a framed knot or link is just a knot or link with a choice of a perpendicular vector at every point. Okay, or and so you can actually think about them as ribbons instead of knots. And we look at all the possible framed knots and links in the manifold. We take linear combinations of them, and then we mod out by these skein relations, which are exactly the Kauffman brackets skein relations. Okay, and in general, this skein module is not an algebra, but in the special case where you have a surface and you have a thickened surface, then all of a sudden you have an algebra structure on there. And basically, algebra structure is just you put one thing on top of the other. Essentially, when you have a three manifold, there's no idea of up or down, but when you have a thickened surface, there is because it's cross 0, 1. Okay, so I just repeated the definition for skein algebra for a surface. And again, this is dependent on which surface you pick times 0, 1. And so here's an example of a multiplication. So I think in my here, this is this V times W is W on top of V, I think was the convention I used here. So, and you can see that if you do V times W versus W times V, you get two different skeins, right? Because this one, the over and under crossing is different. And so when you apply the Kauffman bracket, the over and under, you'll just have the Q half and the Q to the minus 1 half switched. This skein algebra is just from an algebraic point of view, it's like really interesting. It's usually not commutative except for very, very small surfaces like a disk or a sphere or things like that. Or when Q is equal to 1. So if Q equals to 1, then you can see that it doesn't matter which way you resolve, you get the same thing. Did that make sense? Yes. Okay. And what do we know about it? We know that it is finitely generated as a module by skeins with no crossings. It's finitely generated as an algebra. It is Noetherian. It has no zero divisors. We know its center now at a root of unity, or actually not at a root of unity, but it's very interesting. Anyways, from a quantum topologist point of view, the really exciting thing about this skein algebra is it's got a very, very it's got a connection with the SL2C character variety. And I was going to say it had a strong connection, but I don't know how explicit it is. I'll try and convince you that it's reasonably explicit, that we can do things with it. Any questions about the skein algebra? I'm going to move on to some hyperbolic geometry. No. All right. So the SL2C character variety is essentially the so let me erase this. I'll draw some more pictures. Okay, so it's the space of all homomorphisms from the fundamental group into SL2C. And we're looking at the character variety. So we think of two homomorphisms as the same if they have the same trace. So hence character for character variety. And the nice thing about this is that it's, like I said, relationship with the hyperbolic geometry is baked in. So SL2C, if you do PSL2C, that's just the isometry, orientation preserving isometries of H3 hyperbolic 3 space. And so actually what happens is that every such homomorphism, well, almost every such homomorphism from the fundamental group of the from the surface to SL2C corresponds to this thing called the pleated surface in hyperbolic 3 space. Okay, so I don't know. And by Thurston's hyperbolization theorem, if phi is pseudo-Nosov, then this mapping torus has a unique hyperbolic metric that's complete. And that complete metric, if you look at the monodromy, corresponds exactly to injective homomorphism into PSL2C with discrete image and whose action is invariant under phi. Okay, so essentially what this is saying is that if you have a homomorphism, like a point in the character variety, in some way, okay, there's this issue about PSL2C versus SL2C, but if you're willing to brush that under the rug just for a moment, then every point in the character variety corresponds to some hyperbolic metric of the mapping torus, okay, corresponding to this surface diffeomorphism. Okay. And that's just all classical geometry with no quantum whatsoever. All right, so maybe let me put this slide up and then I'll explain this a little bit more. So when Q equals 1, so then it was, so, okay, so let me write this. In SL2C, there's a trace identity that says that if you have trace of M, trace of N, this is trace of Mn plus trace of Mn inverse, okay? And what Triav, Bullock, and Bullock, Froman, Charlie Froman, Joanna, all these people realized is that this trace identity is remarkably like the skein relation. So the skein relation, not quite, says that, okay, if you think about this curve as trace of M and that curve is trace of N, this is the same as the trace of M and then N plus trace of M and then N inverse. Okay, so somehow they took this equation and they converted and showed that it's essentially the same as the skein relation. For technical reasons, I should put minus signs here. And there should be some kind of, there's no crossing here. So Q is equal to 1. This is very technical and it's just there to make it work. Is it okay if I just kind of ignore that part? All right. Okay. So that's this top one. When Q equals 1, there is an isomorphism, and you can rephrase this using representation theory, that the one-dimensional representations from the skein algebra to C corresponds to a choice of character in the SL2C character variety. Okay, and the proof is this, but much fancier. Okay, and then what Triav realized is that if you, so when that's when Q equals 1, but when you have Q equals not 1, so if you have Q equals not 1, let me draw this under this way, that this is kind of some kind of non-commutative deformation of the skein relation. right? So you have this one. If you deform it a little bit, the skein relation, you put Q's and you have over and under information, then you have that the skein algebra is actually a quantization. Okay, and what Triav did is he looked at K times L minus L times K, and he realized that it's related. Okay, so I'm being messy here. And it's some number, Q to the half minus Q to the minus and half, I'm not sure. Right, and then plus, and if you put in Q equals e to the 2 pi I over h, e to the 2 pi I h bar or something like that, then you get some kind of, it relates to the Poisson bracket on the trace functions on SL2C character variety. I went through that very fast. I'm just trying to get you to get some vague thing that, yes, I believe her that this works. Is that enough? That's all I'm looking for. You don't need to know the exact details, but essentially what it ended up doing was saying that the skein algebra is some kind of quantization of the SL2C character variety. Okay, all right. Now, this was proven in the 2000s, in the 1990s and 2000, up to about 2000 or so. And then actually you can make this correspondence even better. So when Q is a primitive nth root of unity and n is odd, if you look at the irreducible representations, and now they're all dimensions, not just one dimensional, before there was only to C, this actually corresponds to characters in the SL2C character variety up to, and with some numbers at the punctures just to make things work. And this was proven, this is called the unicity theorem. And moreover, that this is one-to-one, you know the dimension of V, and it's 1-to-1 on the smooth part. Okay, and technically I'm lying here a little bit. I think it's proven when it has there's some issue about whether there's punctures or not punctures. Okay, so I think that when the Froman, Kanya, Bartoszynskaya, Lay, they proved it with punctures or no punctures, and they only showed that the correspondence is 1-to-1 on a Zariski dense subset. In Ganov, Jordan, and Safronov, they used something from algebraic geometry, and they showed that the Zariski dense subset contains the irreducible representations, and so, but then they needed that the surface was closed. So if you are willing for me to do some more hand waving, then this is true. And however, so the techniques of Froman and Ganov Jordan were non-constructive. And so what Bonahon and I did actually before their work is that we showed how to go from the representations to the character variety and then the character variety back to the representations using some very concrete, compute, do this construction, but we couldn't prove that it was 1-to-1. Okay, and so they use this theory of Azumaya algebras, central characters, things that I know less about, to show that it was indeed 1-to-1. But then they have different conditions to make all their arguments work. But anyways, for the constructive view, it's actually not too bad. So if you have a representation, then what you do is you want to essentially get the central character. And so to get the central character, there's this operation where you thread by a Chebyshev polynomial, kind of how you thread by the Jones-Wenzel operators, idempotence to get the Jones-Wenzel. This is the other Chebyshev will give you a central element. And once you have the central character, then you just say, oh, that's actually just an SL2C character. So going from this way is pretty easy. And these puncture weights, when you go this way, you just need to make sure that these puncture weights play well with the character and there's some kind of compatibility condition. And then in the other direction, if you give me a character and some puncture weights, I'll show you how to create this irreducible representation. Okay, and actually I will do this because I'll need to do that before I can define my quantum invariant. Okay, you guys ready for more? Okay, so on this slide, I said a whole bunch of stuff, but the one thing that you want to remember is that if I have two characters that are the same, meaning two represent homomorphisms from pi1 of sigma to SL2C, and if they have the same trace, then they will give the same irreducible representation, but it's only up to isomorphism. So this is where I'm going to get that invariant from. So I'm going to make use of that. Okay, so remember I had my 5 steps, right? So let's start off with the pseudo-Anosov diffeomorphism, root of unity. And the first thing I'm going to do is I'm going to pick a character in the character variety that is phi invariant, and it's irreducible. Okay, so remember we'd seen an example of a phi invariant character before. It was associated to the hyperbolic metric of the mapping torus. Is something like that would do this. And so I pick one that's phi invariant, meaning that the characters are the same, or that this diagram commutes. I need not only character, I need puncture weights. So I compute some kind of algebra equation. There's some algebraic equation here. I solve and I pick some puncture weights that are phi invariant. It's very, very mild. It's just a matter of solving something. And then what I do is I run that machinery, right? So remember, let me go back. There's this machinery that goes from here to here, right? So I'm gonna put in R, I'm gonna put in R following phi star. So I do it twice, right? I have puncture weights, I get a representation of, I do it again for R following phi star, I go this way, but these two guys were the same, right? And so these representations over here are gonna be isomorphic. Again, I haven't really defined it, showed you how to compute any of this yet, but I will. And so these guys are isomorphic. That means that V and V are essentially the same, right? Up to some kind of change of basis matrix, some kind of intertwiner. And so there's a change of basis isomorphism. It's going to be, by Schur's lemma, it's going to be unique up to scalar. So I'm going to pick so that the determinant is 1. And then I take a norm, and then all of a sudden I have an invariant. And I've made a bunch of choices. I had my original phi, I have my root of unity, I have my R, which is phi invariant, and then I have my puncture weights that dependent on R, right? So there's a lot of choices that I've made here, but I claim that it's invariant for that. Okay, so just a quick note that these phi invariant, so I was given the pseudo-Anosov diffeomorphism, right? And then I needed to pick a phi invariant character. And as I said, that there were many examples there's an example of this that corresponds to the hyperbolic metric of the mapping torus, right? And because I'm going from PSL2C to SL2C, there's lifts, but there's a whole C-dimensional family of such things, and those correspond to hyperbolic metrics of Dane fillings along Dane fillings of the mapping torus, okay, along the puncture, along the cusps. Anyways, so here in my picture, it looks like I just have one hyperbolic metric, but there could be many lifts, and so then there could be many of them that are correspond to the hyperbolic metric of the mapping torus. So now let's go back to the conjecture. So the conjecture says that if you start off with the pseudo-Anosov phi, you have a sigma and it's possibly got punctures, you pick your Q, and we're always going to pick the first nth root of unity, and n is odd for us. I pick an R that's phi invariant, and here the key is, remember this whole family of them. It doesn't matter which one I pick. I just pick any along that blue curve, any that is phi invariant. These might correspond to hyperbolic metrics of the Dane fillings of the mapping torus. I pick puncture weights, and I have to pick them consistently, so I always pick the right one. So that, and mostly it's just so that my formulas match up. Then what this says is that if I take the quantum invariant that I just defined, right, the determinant 1, I have that change of basis matrix that changes the determinant 1. I look at its asymptotic growth as n goes to infinity. Then I claim that it always picks up the hyperbolic metric of the mapping torus. So I have this whole curve, remember I had that blue curve, right? And I pick any point around the blue curve, and you look at the asymptotic growth rate. It, Francis likes to say, it smells the hyperbolic one, okay, from afar. Okay, so we have been working hard to try and prove this, where sigma is the one punctured torus. And so far we need some extra conditions, but we're still working on it. So here's some nice pictures. So if sigma is a one punctured torus, then the mapping class group is either Dane twist bound one way or the other way, right, or on the longitude or meridian. I think if you're thinking in terms of matrices, or this is the mapping class group is SL2Z, right, then you can have one, there's the upper triangular one and the lower triangular one. So one's L and one's R. And the mapping torus has volume 0.21, blah, 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 blah. And we plotted this invariant, right? And so you can see as n goes to infinity, it closes in on this line, which is the volume. And then same thing here, right? And these two correspond to different choices of initial choices of character and puncture weights. And they still both. And so we ran a bunch of calculations like this. We've also proved it in the very, very, very simplest case, where the mapping torus is the figure 8 knot complement. And here I say it's the simplest one because it's the smallest, simplest pseudo-Nosov diffeomorphism for the one punctured surface. It's one Dane twist this way, one Dane twist that way, and you get the figure 8 complement for the mapping torus. Okay, so what I'd like to do is kind of run a really, I don't know how much time I have, another half hour, right? Or no, 20 minutes, right? So I'd like to go back and show you a little bit about how to compute this trace, in this case for the figure 8, just so that I'm going through this like 3 times now, right? So I gave you like the really, really short recipe, and then I said, here are the 5 steps. Now I'm actually going to start computing. So you'll just see it over again. All right, so I believe in repeating things over and over again. Okay, so how do I compute? So in this case from now, I'm going to pretend like the surface is just the one punctured torus, but a lot of this just carries through even if you have Heinrich genus. Okay, so these irreducible representations that we go, remember we work character to representations. Actually, we did it by going through this thing that's called the Chekhov-Fock algebra, and it's an example of a quantum torus. The algebra is super easy so that when you write down the representations, it's also super easy. And the really nice thing is that there's this quantum trace map that goes from the skein algebra to the Chekhov-Fock, okay, and it's injective. And okay, it's not very easy to compute, but it's computable. There's like a formula for how do you do, right? And so let's see, so there's this quantum trace map, it's injective. From the representations of this Chekhov-Fock are classified, and they're classified exactly from earlier work, exactly by the representations of the characters in the character variety, and there, like the hyperbolic geometry is everywhere in this representations when you look at the matrices, and I'll show you in a second. And so when we look at phi sub r, and then so what was the point of this? Give me a second. All right, so I'm constructing skein representations of the skein algebra. And so, so what I do is I inject it into Chekhov-Fock. The representations of Chekhov-Fock are classified according to the character and puncture weight, which is exactly the same data. And so I have these ones are all classified. So I just compose to get the whole thing. Okay, so this is the whole, the slide where it was the double arrows, right? This is the character variety, and then this is going to tell me what the representation of the skein algebra is. So this is that unpacked. And every diffeomorphism of this one punctured torus is either a product of Dane twists, right? Either the longitude or the meridian in some order. And so what I'm going to do is essentially for every one of those, either it's a L or a R, then I come up with a matrix that corresponds to the change of matrix for that Dane twist. And then essentially I'm going to have a whole bunch of matrices one for L, one for R. I multiply them together. I have some kind of T twist at the end to make sure everything works out, everything aligns. And then I just multiply matrices, compute the trace. Okay. All right. Does that general outline look okay? Any questions? Okay, here comes the definition of the Chekhov-Fock. All right, so the Chekhov-Fock algebra is a quantum torus, and usually the generators correspond to the edges of an ideal triangulation. If the edges are far away and they never see each other, then they commute. And if they're next to each other, then you look at how many times they're next to each other, whether it's on the left or the right, and then they Q-commute depending on that combinatorial information. Okay, for the once punctured torus, it's super easy. So here's a once punctured torus. I didn't put the arrows in. And it's got an ideal triangulation with 3 edges. So in my Chekhov-Fock algebra, I'll have 3 generators, X, Y, and Z. And in this case, let's see, X is on the left of Y twice, right? Once up here and once down here. And so I get a Q to the 4th over there. So there's some kind of, and then so it's 2 times the number that it was on the left or right of the other one. And then I have these. So it's in terms of an algebra, this is super easy, right? Like there's hardly anything going on right here, right? Which means that its representations are also going to be super easy. Okay, and so it turns out the representations are just going to be, so I guess you have to choose a little bit. So every irreducible representation of the Chekhov-Fock is isomorphic to a standard one. And the standard one takes X to a diagonal with Q's down the diagonal. Or, and then it takes Y to, oh wait, it's a scalar multiple of Q times the diagonals. A scalar Y times one where it's shifted, right? It moves, it's a Q permutation. And then Z per Q permutation in the other direction. And if you multiply them all together, you get a scalar of the identity. Okay, so super easy. And not only that, if you have any 2 such representations, they're isomorphic if and only if these scalars have the same nth powers. Okay, so so you're going to have the diagonal one, the diagonal ones are going to be okay. Any questions about that? Okay. So these, so I said that so apparently, right, so what Bonahon and Liu figured out is that these representations, this data that you need to build one of these representations corresponds to hyperbolic geometry. It corresponds to a character in the SL2C character variety and puncture weights. And I can tell you exactly where they are. These X, Ys, and Zs, those are going to give you the hyperbolic geometry of some pleated surface in hyperbolic 3 space. That H corresponds to some kind of the puncture weight that around every puncture, okay, because you're going around X, Y, and Z. It's not quite that, but it's close. Anyways, so those X, Y, and Zs are complex numbers, and you can think of like embedding the torus, one punctured torus, in hyperbolic 3 space. Let me try and draw a picture here again. Here we go. So I'm going to think of hyperbolic 3 space as the upper half plane, upper half space, right? And so I'm going to put in, so I have say 0, 1, and then infinity. So there's a triangle, okay? And then and then I want to put in another triangle. And when I put another triangle in hyperbolic 3 space, I have I could kind of glue it here, and then there's some kind of, I can't draw this. There's some angle here and some shearing, right? So you can put, oh, my picture doesn't look like they're bent, but they're bent in space like this, and you can have some kind of shearing along that edge. Okay, so there's a bend and a shear. And let's see, the bend is the angle of the argument of the complex number. And then the shearing is the real, is that the real part or something like that? I'm getting it wrong. But in any case, this those numbers X, Y, and Z tell you the shear bend coordinates of the pleated surface in hyperbolic 3 space, and they correspond exactly. So they're classified by the characters that come from that. And then there's, remember I was talking about there's this extra thing to make things match up. There's this operator. So if the nth powers are the same, right? Then they're isomorphic, and so there should be some isomorphism. That's what I call the twist operator, and it just conjugates from one standard one to another standard one, I mean, that are isomorphic, right? So meaning that you conjugate by T, and they're the same. And because it's all completely explicit, right? You could just compute this, right? Do you guys believe that, right? So I just look at these matrices over here, and I say, oh, I have one, I have another, they should be conjugated, and then you just write down a matrix for them. So there's the matrix for T. Okay, so now I'm going to go back and compute the matrices for L and R, Dane twist one way, Dane twist the other way. So, so it's just, again, a computation, right? I run the same scheme through, right? So I embed skein algebra into this checkoff block. Again, I use this mysterious injective map that's called a quantum trace. Then once I have that, every character will give me these numbers X, Y, and Z, and H, right? And then I create a irreducible representation right here. And then I compose to get a skein representation of the skein algebra. I do that again, but this time I'm going to use R following L. So I use the same thing, but then I do a Dane twist to it first, and then I compute. And these two things have to be isomorphic. And again, this is all a matter of like writing down matrices. You get a change of basis matrix. I compute it, okay, and it looks like that. Okay, it's got some lots and lots of Q's and Y's and Z's, and actually here we just use only Y, right? So X prime is 1 over Y. There's some kind of change of basis, and then you have these things. Each term in there has these things called the quantum dilogarithm. And this is what's really cool, is that the classical dilogarithm is related to the volumes of ideal triangulations, of an ideal tetrahedra, right? And so this is where that volume is going to start coming up, okay? So I'm not going through very, very carefully, but just so that you get a sense that, okay, this formula has some kind of like hyperbolic geometry baked in. And then you do it for the R. And then, so if you want the whole intertwiner, you take, so if this was an L, then you take the L matrix. If it's an R, you put an R matrix here. You have a bunch of matrices, you multiply them together. You need the twist operator at the end just to make sure that you get isomorphic at the end, and so you want to kind of make sure the head and tail match up, and then you get it. That's it. So if you have say LLR, then you're going to be multiplying 3 matrices plus the twist, and you get it's not surprising, you're going to get a nested sum of 3 things, and then the terms will have 3 QDLs in them. Okay, and it's just this mess of stuff. But in the mess of stuff, these numbers U1, U2, U3 carry some kind of hyperbolic geometry information. All right, so that was the computation. Now I'm going to go back to the easiest case, which was the case of the figure 8 knot. And in the figure 8 knot, remember it was the smallest one. There was just one L and one R. There were only 2 things. And so you have a double sum and 2 QDLs, and for some whatever fluke, the nested sums separate, and so they factor. And then they factor like this. And so now if I wanted to prove that the asymptotic expansion, right, and not the asymptotic expansion, the asymptotic growth rate, so this is E to the something up there is related to volume somehow. Okay, so that's what I'm going to do next. All right, so here's the thing that I want to do. I want to show that if I took that double sum that I had before that factored, then I look at it's going to be E to something, and the something up there is going to be, as n goes to infinity, will be the volume. Okay, so, and what's also nice is that the figure 8 complement is made up of 2 regular ideal tetrahedra, and each of the volume is this function 3 Lobachevsky pi over 3. Okay, and this Lobachevsky is related to the classical dilogarithm. And now we have a quantum version of it. Okay, so let's see. You guys remember? Okay, so here, this was 1L and 1R. It factored. Each of these sums looks essentially the same, right? They have the same kind of format. That L0 and those M0 correspond to the twist operator, so they're not the same. But and then the U1 and the U2 aren't the same, but they look kind of the same form. So if I figure out what the asymptotic growth rate of one of these sums then I'll be done. Okay, so when Q is a root of unity, that QDL here, that was these numbers that we saw in the matrix, right? For the Dane twists. They were just all over the place in the matrix. And they are products of 1 plus u q to the minus 2k plus 1. So they're over 1 over u to the n to the 1 over nth power. And these u's are related to like shear bend coordinates of a pleated surface. When n is sufficiently large, you can prove that it'll be e to something, and the something up there will involve this Lobachevsky function. Okay, and remember, Lobachevsky function is related to the volumes of ideal tetrahedra. And then there's going to be a function in front. And this is for n sufficiently large. And actually in the limit, if you stick this, allow a factor of q in front, actually you can rig it so that this thing, this a becomes a plus or minus b function, and this b function is a positive real number, and the whole thing is real. But this is as n goes to infinity, right? So this is far out. So now, okay, I just repeated the previous slide. And so if I have this QDL in the sum, and then I have a q to the 2j squared in front, you get some real function, positive real number, and then e to some Lobachevsky, which is related to the volume of ideal tetrahedron. It turns out that these are going to be plus or minus. If it's a plus in front, it turns out that this whole sum, you'll pick up the largest term. If it's a minus, then they kind of cancel out in pairs. And I think I have enough time, so maybe I'll show you some pictures at the end. In any case, what happens is that, okay, so these cancel out in pairs if it's a minus. If it's a plus, we're going to get this largest term, which involves the Lobachevsky. Okay, so I'm going through this pretty fast. Okay, so I have some number in front, and then 2 of these sums multiplied together. That number in front, we do a lot of basic calculus arguments, right? It's basic calculus, but it's not trivial, right? You can show that it splits into 2 convergent subsequences according to whether n is odd or even, but in any case, it converges. So when you look at the asymptotic growth rate, that just goes out the window. We can ignore it, right? And then from before, we know that each of these sums is e to the something, and the something up there was the Lobachevsky function, actually Lobachevsky of pi over 6. And so if I multiply these 2 together, I should get 2 of them, right? And so if I took the, let's see, e to the 2 of them, I divide by n, right? So I have Lobachevsky pi over 6, 1 over 2 pi, but I have 2 of them. So I have 1 over pi Lobachevsky pi over 6. Everyone okay? And then it turns out that the Lobachevsky pi over 6 function is related to the Lobachevsky pi over 3. And actually there's 2 of them. And so then you get the ideal volume of an ideal tetrahedron, and you get exactly the volume of the mapping torus down here. Okay, looks like I always go too fast. So here's some references. Let me show you some nice pictures. All right, so here's the picture for the figure 8. Remember I said that if it's positive, then you get the biggest term has the Lobachevsky up at the top, and then otherwise they cancel out in pairs. So actually here there are 7 petals. Let's see, 1, 2, 3, 4, 5, 6. Wait, 1, 2, 3, 4, 5, 6, 7. Sorry, I can't count. And definitely you can see that these guys all cancel out in pairs. And this one is the one that doesn't cancel out. And the very tip of that is the biggest term, and that's the one that'll give you the Lobachevsky. Okay, and so that's very nice. Do you guys want, I have time for one more picture. So one more picture, here is LLR. So remember this is 3, and I nested sum of 3. And now if I plot these terms here, it's this horrible mess, right? And so because it doesn't factor, then things get crazy. And so what we're trying to do now is to do Fourier analysis on this, to separate them into different modes of, because they're all periodic. And then we do this thing from the physicists called the saddle point method to make sure things go through the critical point and that it picks up the volume. It's crazy. So we're working hard on it, and hopefully we'll get, right now we need some extra hyperbolic geometric conditions to make it work. And so we keep on thinking, okay, we could relax it. And so we're trying to do that. And so that's this third paper that is coming soon. Anyways, I'm happy to take any questions.
So questions for Helen?
Go first and someone send a micro.
Okay.
Yeah.
This is a bit of a vague question, so it might not make some sense, but I just happened to notice that this trace looks like an average, right? It seems like a Monte Carlo computation of volume.
Oh, I don't know about that. I don't know.
Because it seems that that's what you're doing, and you're like looking at a different basis because you're doing like Fourier analysis. These are like calculations because the root of unity is exactly what you do when you do a Fourier transformation. So I don't know, these matrices, you should actually be looking at the logarithm of these matrices and
That's right.
doing some change of basis. That I don't know. But it seems like, I don't know if there is some work in this direction,
yes.
but it seems that that's more or less what they see.
Yeah,
It's
so that's
like an
exactly
average.
what we're trying to do, is to kind of take Poisson summation formula and change the basis so that you can see what's going on and the contribution of every one of the Fourier coefficients. But the idea is that to tie it with hyperbolic geometry, there's like the Atsuki's strategy is that you do a Fourier analysis, and then some of the Fourier only a few of the Fourier coefficients dominate, and the ones that dominate are the ones that carry hyperbolic geometry. And so somehow it should work, but then the analysis is really hard, like those estimates, and making sure that you do everything right.
But also the algebra, it seems like it should look at the logarithm of this algebra somehow.
Yeah.
Because that's why you have all these complicated terms. It's like working with the Weyl algebra instead of a Heisenberg algebra in quantum mechanics. I don't know. I don't know. I just wanted to comment because it seems like that kind of computation.
Thank you.
That's it.
So, is anything known or either known or expected about the next terms in asymptotic expansion, like the subleading terms?
I don't know. Do you, Tian? I don't know.
I guess there's something with torsion.
Oh, yes, there's.
And also the phases.
Yes, there could be the torsion, and the phases should be connected with the Chern-Simons.
Yeah. So, for example, the teal thing is definitely got some right-amide. It's related to right-amide torsion.
Okay.
And I don't. Yeah, the phases must have some.
So it really. So then you're saying that this really is kind of secretly a Chern-Simons path integral.
Yes, I think
that's
so.
given both the formulas. Okay.
Yeah.
So I don't know how many knots. I mean, because I don't know this type of thing. I don't know how many knot complements are mapping tori, but does this give a new way of getting the Kashayev volume conjecture?
So for the once punctured torus, so if it's so hyperbolic, so if you have a hyperbolic knot, I think you need the ones that are fibered are the only ones that are mapping torus. So there's not very many of them.
Okay.
Yeah, so for the once punctured torus, the figure 8 knot complement is the only one. All the other mapping tori are Dane fillings of it.
So I guess conversely, if somebody did prove the Kashayev volume conjecture, would it does this one, does yours follow?
So that's an open question, how our quantum invariant relates to the colored Jones. We don't know. So what we do know is that, let me go back. It's kind of this thing that we always think we don't know how it's related. So all the way back, give me a second. So here, if you pick the identity character, so the one where you take every loop in the fundamental group and you send it to the identity matrix, then that corresponds to the Witten-Reshetikhin-Tarayev representation of the skein algebra, but it's not no longer one-to-one. So we know that if you start with Witten-Reshetikhin-Tarayev, you get to the identity, but then if you go back this way, we think that probably there should be more than one, and we don't know what the other ones are. So even here, before we do any quantum invariant volume conjectures thing, there's like the identity character. It corresponds to something we know that's interesting. And then now there's all these other representations of the skein algebra around it. And I think they must be related to the non-semi-simple TQFTs that Christian was talking about. We don't know how exactly they're related. So to answer your question, we don't know anything. So all we can say is that if you rephrase it, then maybe there's some hope of proving this other one, but then tying it back to the Kaishai.
In the case where you take so there are another thing, for example, a periodic diffeomorphism, do you have something to compute which is interpreted in terms of?
I don't know,
asymptotic?
because if it's periodic, we can still create these representations. But they're going to be like that. If you start off with the identity character, there's so little there, right? Like I think the asymptotic growth should be like, there should be no asymptotic growth is my, right? So that's my guess, but anyway.
So you can also treat, I mean, you're taking the large n limit, but also at the same time q to the b and e to the 2 pi I over n. So my question is whether you could also take different limits, still large n, but q just going to some number on the unit circle.
So we ran Mathematica calculations, and we think that some will give you also this asymptotic, but not all of them. And we don't know, we don't have a firm conjecture.
But it converges for many.
I think, yes, there are other routes where it should converge.
Yeah, because for these not invariants, this large n limit has this story that at least if you look at the tail, has this nice quantum modular properties, right? And this is a nice guiding principle. So
yeah.
have you looked at this?
No. So at least for the volume conjecture, right? So if you, I think, okay, correct me if I'm wrong, but like there's a conjecture that due to Witten that if you pick so for these Witten-Reshetikhin-Tarayev invariants, if you pick some root of unity, then it's polynomial growth. But then it's also conjectured that if you pick a different one, so I think that's Tian Yang and Mauricio Romo and a bunch of them, then you get asymptotic growth, and that there's something there, that it's 2x volume. We don't know what's going on. So we've just done it for this one, and then there's some evidence, but it's not enough so that we can be like, yeah, we're going to make a conjecture and write that down and put our name on it.
Okay, there are no more questions for Helen. Thanks, Helen.
Thank you.